I'd like to welcome everybody for today's webinar brought to you by Dlubal Software. Today's webinar is about designing thin-walled steel structures with shape-thin and RF-FE-LTB. This webinar will be presented by Chelsea Jennings, support engineer by Dlubal Software, and myself, Walter Rüstler, also from Dlubal Software. Before we start with live demonstrations of the two modules, I'd like to give you some organizational hints for those who are participating the first time. You can hide and show the control panel with the red arrow on your webinar software pane to the right, and you can use the chat options to ask some simple questions below. We will go through those questions at the end of the webinar and also try to answer them as best as we can. If we should not be able to answer them, we will get back to you by email, and we will also record this webinar so you have the chance to view this webinar online later on. Shape-thin is the first module we're going to present. It is a module that you can use to analyze section properties for any thin-walled sections. It doesn't matter whether it is open or enclosed or a mixture of it. It comes with a graphical user interface, and it enables you to draw up cross-sections in a general way. Typical sections that are most likely in the analysis software you're using that come with it are, for example, eye sections or channel sections or angles. You usually can pick from a library, but for sections that are made, custom made, that are maybe cold formed or welded together or built up from different standard sections, you may use shape-thin to get the section properties. Shape-thin also allows to enter internal forces and to get stress analysis. It includes warping, and it's also capable of checking for local buckling and analyze the failing section parts on a cross-section. It comes also with a classification according to Eurocode for general cross-sections, and it has plastic design options. It also is capable of importing internal forces from RSTOP RFEM, or you can, as you like, manually enter some internal forces. We will see this module live, presented by Chelsea in a few minutes. The second module that we are going to take a look at is RF-FE-LTB. It is meant to do buckling and lateral torsional buckling analysis for according second order. So it's made from a 7 degree of freedom 1D finite element, which includes warping moments. In general, you find in the codes procedures how to check for stability for standard sections, like for an eye section, but once it comes to a general section, there's not many regulations that you can use. In general, you have to use such a program like RF-FE-LTB, where you can set also loads eccentric, and that includes the 7th degree of freedom, the warping degree of freedom, and with an imperfection and a theory second order analysis and a stress analysis at the end, you can check for the allowable or limiting stress, and if the critical load factor is smaller or larger than 1. As I said, it works for all kinds of sections. It allows to place loads eccentric. Also, it has the option to stabilize section eccentrically, so you can arrange a support or a spring along the top flange, for example. And it does stability and stress analysis. We will also take a look at this module live. Shape Thin and RF-FE-LTB work together with RFEM. You can import cross-section data from Shape Thin to RFEM, and RFEM also is used as a modeling and housing tool, I would say, for RF-FE-LTB. At this time, I would like to change to the live demonstration of Shape Thin, which is done by Chelsea. And Chelsea, I'd like to ask you if you're ready, and I hand you over the controls.
Thank you. I am ready. I'll go ahead and show my screen here. Hello, everyone. Thank you once again for joining us today for this webinar. My contribution for today will be an introduction into Shape Thin by going through a couple of examples of modeling and analyzing non-standard sections. If you can see my screen now, I'm in Shape Thin, and the layout of the program is similar to RFEM in that you have a graphical window and workspace. Below that are tables. To the left here we have a navigator, and at the top there is a toolbar with several tools for modeling and also for displaying the results. So in Shape Thin, when you are creating a new file, you have some options here in this dialog box. First, you define the name of the section, which is also the file name, and you can also add a description, which will appear in the heading of the printout report. Below here, you can see some options for calculation. Here you can define if you would like plastic section properties to be determined. You can also perform plastic design. You can check limiting ratios according to DIN, and also check or analyze the effective cross-sections. To the right here is just an option where you can define the direction of the global coordinate axis. Okay, one last thing before I start with my example, I'd like to take a quick look at the project manager. This comes with Shape Thin and is a nice way for you to be able to quickly access and organize all of your files and previous sections that you've created. Here is a preview of my first example I will be creating, and here's a preview of the second one, so you can keep that in mind. Okay, so getting started here, my first example will be demonstrating one of the ways in which you can create sections in this program, and I'll be making a built-up column section out of standard I sections and then modifying them. I will be creating an opening and modeling some welds. So first I'll go ahead from the toolbar, open up the cross-section library, and here I can choose my I section for my first part of this. So I'm going to take an IPE 500. And this dialog box that appears is what facilitates you placing the section. So since this is my first one, I can just go ahead and place it so that the top flange is at the center ordinate. Okay, going back into my cross-section library, I can choose an HEA 220. And here I'll use this section, or this dialog box a little bit more. I want to define a rotation, as if you saw from the preview. I'll have a rotated I section attached to the web. And here is where I define which part of the section I'm deciding my placement by. So at the moment I have the center one selected, so if I go to the window and pick this node here, the center will be placed there. So first I want to go in and choose the one on the left side, and then, one moment. Okay. I can go ahead and choose where it's going to be placed on the section that is already been placed. So here I pick the element that I want on the edge on the right side, and so there you can see it's locked on the right side of the web here. And I can just place it in anywhere, or I can select my distance from here. Okay, and hit OK, and there I have it placed. So now I have two standard sections that can be selected independently. If I would like to show the section details, I can go ahead and display them from this dialog box if you need to reference that at any point. Okay, so as I said, I'd like to make some modifications, add an opening. In order to do that, I need to be able to select these parts individually. So if I make the selection of the entire element, right-click, and select Reduce Section into Elements. So now I'll show you exactly, letting me know I have 5 elements and 4 point elements. So here I'll go in, zoom in. You can see that each side of the flanges and the web each make their own element now independently, and the curved parts are point elements as well. So now I can select the web, right-click, and choose to insert an opening. So here, define my width of the opening. I want 30 millimeters, and its location. I want it to be 60 millimeters from the start of the element, which in this case is the right side. So apply, and I have an opening placed. When an opening is defined, what is put in between is a rigid dummy element. And for our calculation, it's, we have a value called the effective thickness, which is for the shear transfer. And so the recommended assumed thickness is the average of the neighboring, the thicknesses of the neighboring elements. So in this case, the web here is 7 millimeters, so I'll make the effective thickness 7 millimeters. Okay. So next I want to model a couple welds at this connection point at the top and bottom. So for that, I'll go back up to the toolbar and select a new point element. And this is ready to go. I have my radius at 10 millimeters, and then I can just select which node I want to place it at, and there I have my, my weld. If I go up to the top, I can make a rotation, negative 90 degrees, and place the top weld there. So now these, the area of this weld element here will be included in the total cross-sectional area. Okay, so at this point I have all of my section modeled. What I can do before I do my calculation is I can do a quick plausibility check. And with this check, it will find if there are any errors. And if there are, it will tell you exactly what is the problem, so you know what to fix. So plausibility check, no errors were detected. Okay. And now we're ready to go ahead and run our calculation and get our results. Okay. So the first table you see here is the section properties. And here's a list of all of significant section properties that have been determined. You have your shear areas, cross-sectional area, position of the centroid, and so on. And you can define what is included in this list by using a filter here. You can include even more properties as well. Okay. Next table that is available is the statical moments. This is the numerical results. And these results are also included in your graphical layout. So I'm going to turn this back on, and you can see the what do I have here? The statical moments in both directions, and your normalized warping ordinance, and then also your statical warping statical moment as well. Okay. One thing I'd also like to point out in the tables here, before you get to your results, you have a table for forces and moments, internal forces and moments, for if you want to perform a stress analysis. And these values can be imported directly from RSTEM or RFEM, or they can be manually placed. So I'll go ahead and just add a couple load cases just so you can see at 0x location. You can do it at multiple x locations. I'll add a compression force of 80 kilonewtons, and then bending moments in both directions for the first load case. And then my second load case, I will add smaller axial force and then bending, and then in the opposite direction for my last bending. Okay, and so now when I run my calculation, a few more tables appear here at the bottom. And here you see the values both in tabular form and graphical distributions. So I have my normal stresses, my shear stresses, there are none here, I didn't have any shear forces, and also your equivalent stresses. Okay, so going back to my graphic here, I can include these images of the results in my printout report if I'd like. So I'll show you, I'll go ahead and take a picture or send a picture of the effective stresses to the printout report, and I'll set it at 50% of the page, and then send also the normal stresses, also at 50% of the page. And I'll open it on OK. And here we have our printout report. Comes with like the default setting. It has a image first, and then your tables of your input data and also your results in the same order as they appear in the program. And below you can see the images that were included. You can customize exactly what information you want to include in this dialog box. You can reduce the amount of information that's included. Another nice feature of ShapeZen is that for a quick summary of the section, your input data, and your section properties, there's an option to create a so-called short form printout. And this is usually, it's one page, and it's usually sent directly to the printer. But just to give you, just to let you see what it is, I'll go ahead and append it to my document I already have. And so this is the page here. It's just a one-page sheet with an image of whatever you have displayed at the time that you send the print, and a table with your input data and then your section properties that have been calculated. So that's nice to have. Okay, so that's all for my first example. I'll go ahead and get started. My second example, if you remember from the quick preview I showed at the beginning, it's a symmetric section that will be used in a rain gutter system. And so for this, I will just draw it in manually using the element tools in the toolbar. So to get started, here you define your grid. I'm working with or your reference point in the grid. I'm working with a 2 centimeter grid spacing. Also define your thickness and material, and then you can just draw it in to the grid. My second line here, I want to be 5 centimeters, but because it's in between my grid spacing, it's a little easier for me just to type in 5 centimeters as the end node there. So it appears, and I want to continue on from this node, but again, it's between the grid spacing. So what will help me is if I adjust my grid origin to be at this node. Now I can continue on directly from here. I want the height to be 16 centimeters. And then the width of the trough I want to be 30. And so because I have my reference, you can see in the dialog box my reference is at absolute 0. If I change it to the grid origin, so now this is the 0 line for Y, I can go ahead and place it at 30. Okay. And since it's symmetric, I can just do manually 1/2 and then make a copy of the rest over. First, I'd like to shorten this line from 4 centimeters to 3. A quick way to do that is to go into the table, find that line, and adjust the coordinate that way. Now it's shortened, and I'm ready to select and make a copy. So going to the toolbar, I have the mirror option. Create a copy through the Z axis, and select the center of this trough line that I have here. Okay, so just like that, I have my full section, and I can go ahead and run the calculation. First, I'll just do a plausibility check to make sure I have all of my elements connecting. Everything is okay, and I can get my results. Again, you see right away, table with the section properties, and your statical moments and warping constants there. Another thing that is nice to include in your documentation is dimensions, an image of the dimensioned section. And so I'll show you how you can do that quickly. I can turn off the view of my results and use the dimensioning tool here. And very quickly I can just select to show the heights of these lines and also do the horizontal lines. And this is also a nice way to quickly make sure you've made all your lines the right length. And here you can see, if you check the table, I believe I made everything is okay, so I think I just made a bad selection with my, I can't select this, but here we go. I just made a bad selection for the dimensions, so let me just try that again. Yes, everything is okay. And so as I said, this can be included in your documentation, so I can just send this once again to the report. 50% is a good size for these this type of image. And then there I have a dimensioned drawing of my section to include in the documentation. Okay, so this is all that I had to show you regarding a couple different ways in which you can model in Then. It's also possible to import a DXF file to use as a template, so this is what Walter will cover, so I will save that for him. Walter will also take you through a few more hints with working in Then and continue with the section on into RFEM and also present the module FE-LTB. So thank you very much for your attention, and I'll go ahead and let Walter continue from here. Thank you.
Thank you, Chelsea, for showing Then. I'm continuing, as Chelsea said, with Then and our RF-FE-LTB. What I'm going to do next is I'm going to import into a new Then model a DXF template. Therefore, I open a new cross-section. I name it with a number in this case, and I stick with the default template. And I have here an empty file. As you can see, you can open several files at the same time. I use now the bottom three here, and material is already selected as steel S235. If I want to import a template, I use the File menu, Load DXF Template. The DXF template can be from any DXF file. You find those files typically from the makers of such sections in the internet. You can download CAD templates, and I used one of those from a cold-formed Perlin maker and saved it as a DXF file. Once I import it, I get a small preview dialog. I can first of all show and hide the different layers. In those DXF files, typically there are all kinds of lines and texts and explanations, and you have the option here to select a certain layer where is the information that you like. Also, I can automatically assign to this layer or to those elements a thickness that I enter here in the text box of 3 millimeters. After that, I can grab the template at the center point origin and then just drag and drop it into the main Then window. And at the mouse click, I have here my complete structure already generated. What I see here also is I have so-called arc elements. If I double click on it, I see the radius of those elements and the thickness and so on. So it's just as like a straight element, as Chelsea showed us. There are also arc elements possible. Here in this model I had, there was an opening for bolts. and because I'm going to use this cross-section to model a three-dimensional or a 1D beam, but in 3 dimension then, I don't want to have this opening along my beam, so I close it here because the bolt holes are typically only a local problem. So I can just click and drag the nodes to the next connecting node and it will automatically connect. Okay, my cross-section is then ready for analysis. I run the analysis and I get the tabular information of the results as Chelsea showed. Interesting for me are the section properties, and I can display them, for example, also on the side of the window, and I can go through the graphical results by showing the different results here. I notice here there is some little problem where I can close the tables. I don't like to see them here. Where the flow of the diagram is not continuous. The sign of the result may depend on the orientation of the individual elements. So if that's the case, I can click on the element, right click, and I can use the command reverse direction. And I do the same thing here because here we had the same problem. Reverse direction. And if I analyze the structure again, now I see there's a continuous flow of the results and it forms a nice picture. Okay, with this I also get here, for example, the rotation of the principal axis. If I want to know how big that angle is, I can show the table and there should be the inclination of principal axis minus 15.87 degrees. I save the result in the file 10-2 and I go to RFEM. In RFEM I will also create a new structure. What you see here is the final result of what I'm going to do now. It will be a 5-meter long beam with a linear load on top, and we will do a analysis of the critical load and show some tools you have inside RF-FE-LTB. We start now a new structure inside RFEM, and I can call it sample 2 maybe. It's a 3D structure, and I can model it just as a regular structure that you might have seen in the previous webinars. I create a new member of type beam, and I create a new cross-section and I choose it from the library. In the library, or if I choose I go back one time. If I choose the library here, then I see there's 2 buttons, cross-section programs, shape thin, and another one that we have is shape massive, which is for thick-walled cross-sections. I use shape thin here, and then here I have the option to select my cross-section that I just made. It's 10-2. I can check also the sectional properties, and all the parts are here. It's like a regular integrated RFEM section. Also see the angle is there, so most likely I picked the right one. Okay, material is steel. Couple more OKs, and then I can just enter and select the grid lines and enter the member. It's now 5 meters. You see here, nice feature is that you see the rendering is just like a standard library section, and it's very good visual impression. If I don't want to see it because it's hiding too many other parts of the structure, I can turn it on and off the rendered mode. I need some supports. I create a new nodal support, and I choose a support that is fixed in all 3 directions, and the restraint about the local longitudinal axis phi x. So on OK, I can enter the first node support. I create another one and I make it a fork type support again, but this time I release the fixation in UX direction and again the restraint about phi x. Okay. So this will give me a correct support condition where I can analyze the structure. Next, I will create a load case. I call it full load. I disable self-weight because I will add the self-weight as an external load. And I create a linear load. Create a new member load, global in related to the through mem blanks, and for now I choose 2 kilonewton per meter. With this I have a simple analytical system and I can run the analysis and I get my results. I get deformation because we have a non-symmetric cross-section. Deformation is not straight into direction C. We also have bending moments in 2 directions. So if I show this, we have MU and MV. Maybe I have to point out that we have now the option to use in RFEM either the principal axis for results or the member axis for results. So when we imported the shape thin cross section, it was automatically rotated in such way that the flanges were parallel to the main coordinate system. So, and the main coordinate system is the global XY system, and the local XY system are in line by default. So I have to rotate it by the principal axis. But if I want to see the internal forces, I can switch them into both coordinate systems by those options here. Next, I'm going to do a regular stress analysis with the steel member module for this beam, and I just want to run this load case, and I have a utilization ratio of about 60%, and there is only a basically plain loading for this member. Also the internal forces, the governing internal forces are only, well, for the global axis it would be only MY and not MC, but for the local, for the principal axis, of course, it has 2 bending moments. Okay, we have a utilization ratio of about 60%. Let's just remember this. Next, I'm going to shape thin. Typically, if I have a larger structure, I have many beams, many columns, many members, and I only like to do a design for a part of the structure, let's say for one continuous beam, or for one, maybe a frame, or maybe a column. But it's not possible to do a three-dimensional analysis with a three-dimensional structure in RF-FE-LTP. So we have the topic that we have to isolate part of the structure from a global RFEM model into RF-FE-LTP. The way we do this is I create a so-called set of member, and I can, with a set of member, I can group basically one or several members into one so-called set of member and give it a name. So basically I can combine, typically situation is linear connected members, several linear connected members to one set of member. Here I have only one member, so it's not so breathtaking. But I need this in order to work with RF-FE-LTP. In RF-FE-LTP, I'm going to open it now. I can select then those set of members. Since I have only one, I can select all. It also automatically takes over the loads. So there's one load case, full load. it takes over the materials, the cross sections. I have all the information also here in this module. And the nodal supports, as long as they are defined in the RFEM model. And now I can adjust them and add them or complete them, because in RFEM or in RF-FE-LTB we have also the degree of freedom of warping. So there is also a warping restraint that I can address. The same thing is also with the elastic member foundation. Here I have the option to add elastic restraints, and the special thing is I can give it an eccentricity. That means I can have an restraint on the top flange, on the bottom flange, or on one location along the beam. In RFEM itself, I only can have a restraint on a node, or if it's a linear support on a line, but I cannot place it eccentrically. Same thing is with member end springs. On each member end, I can attach eccentric springs. For example, if I have only a discrete support somewhere along a continuous beam, I could do this. I also can have releases in such structures, and again I have the warping degree of freedom here. The loads are also imported from RFEM. There's different load types that we can use, different load distributions, and if you click here you have the option to pick from the offers here, load direction, and we have the 2 kilonewton per meter imported. Again, we have the option to have an eccentricity, and this is very important if you deal with stability problems. It's a difference, lateral torsional buckling, if the load is on top of the beam or eccentrically, or if it's always in the shear center or in the centroid. Okay, I also have nodal loads and I have imperfections I can work with. I'd like to use the default settings and run the analysis. What we get here is, again, just as in steel, a stress analysis. We have here axial stress, shear stress, and equivalent stress. And now we have also utilization ratio, and you see the difference in the calculation. We have here almost a utilization ratio of 1. And also as a result, we get here the critical load factor. We get 1.71 as the critical load factor. And if we want to have a stability check according to theory second order, we need to have an imperfection, and we need to have a stress check that is with a utilization ratio smaller than 1, and we need to have a critical load factor that is bigger than 1. And then with this we can check for stability. Okay, so without any changes from RFEM, I get those results. We can take a look at the graphical results. For example, here we have the we can look at the deformation, for example, and we can show this a little bit better. If we go to the display tree and check here deformations, we can have here cross-section colored, and you get this nice display where we can also increase the deformation a little bit, and we see what happens to these cross sections. So it's because of the unsymmetry, it's a combination of horizontal and vertical deformation. You can see the top flange is moving sideways and causing all the other internal forces, of course. So we can also take a look at the results. So we have some small axial forces, we have the shear forces in both directions, we have also torsion that we don't have in RFEM, because in RFEM the loads are always the crosswise loads are always in the shear center. And so if we have only global loading, global load direction, there will be no torsion. But in this module, our RF-FE-BGDK, all those effects are implemented. Okay, we have primary and secondary torsion, which comes, and also we have a warping moment. Okay, now we want to go back to our RF-FE-BGDK and continue with our stability check. I'm going next, put the load eccentrically. So I put it on top because most typically the load is imposed on the top of the cross section via maybe a steel deck and so on. So if I pick the eccentricity, I know now where exactly my load application will take place. If I run the analysis again, the eccentricity has a very negative effect. You see the stresses increase because the internal forces change, and also the critical load factor drops a little bit. Okay, what can I do now? We saw that the deformation was a combined deformation from rotation and horizontal movement. If I'm able to restrain this horizontal movement or this rotation, I will have a very good effect, I think. So this I'm trying to do now. I'm going to the member elastic member foundation. I select my first set of members, and now I can enter all the spring constants for those restraints and also the eccentricity, but typically I don't know those springs. So we implemented a tool that gives you the ability to calculate such springs. In this tool you can select what type of restraint you have, whether it is a lateral or rotational restraint. Lateral restraints typically would be trapezoidal sheet. Of course, if you apply such restraints, you also have to make sure that the, for example, steel deck is able to handle those stabilization loads from the restraint. I'd like to apply a rotational restraint in this time from a trapezoidal sheet. I need to give the program the information about what's the span of the support of the trapezoidal sheet and what's the length of the shear panel. I can either pick it. If I have a building, I can pick 2 nodes. In this case I don't have. I just assume here maybe it's 20 meters. The beam spacing should be 1.5 meter. The steel deck should be from a corrugated sheet, and I pick there comes a nice library from some provider, some steel deck, maybe something like this. Okay. All the parameters, effective stiffness of the steel deck are imported. If it is a continuous beam type of mounting of the corrugated sheet, I can also take this into account. Also the rotational restraint from a connection can be taken into account, and there's a table that you can use from Dann that gives you some parameters depending on how many bolts you use to fix this steel deck. So I say the bolt spacing should be the bolts should be in every rib of the corrugated sheet. Okay, and then the last part is the stiffness of the rotational stiffness of the cross section itself. There is also formulas that can be used, but they are only valid for eye and channel sections, and this time I just ignore them. With this information, we analyze the spring constant for a rotational spring, and it's already written in here in this input box. On OK, it will be transferred to the table here. And next, I'm going to select the eccentricity and say, okay, this rotational restraints should act on top of the cross-section as well. Okay, if I do this and run the analysis again, you see we dropped quite a bit in the stress ratio. We're about the same value of 60% that we had from the regular steel module. And also, if you take a look at the critical load factors, we see it's also dropped to 6.32. To make the analysis of second order, stability analysis for according to second order complete, we need to apply an imperfection. This is the last thing I'm going to do. There's an imperfection tab that I can select. And in this case, you might be able to find or to know what the shape will be for an imperfection, whether it's cambering or sway or inclination. But if it's a 2D frame structure, you might not know how the imperfection really looks. It has to be according to the first buckling shape. In most codes it's regulated this way. So our RF-FE-LTB has the option to analyze several eigenvectors, and I can pick the imperfection graphically. That means I can analyze several eigenvectors, and I can take a look at them graphically. If it's too much of a distortion, I can change them. I can change the magnification factor, and you can see here the typical failing modes of such a beam, and I will choose in this case the eigenvector number 2, which is the cambering that I want to have. And this, the horizontal part of this imperfection shape will be applied then to the structure. So I have this graphical view, which is very important to see what type of imperfection I'm selecting. I go back to our RF-FE-LTB, and now I need the scaling value for this imperfection. I need to have the pitch value basically of the imperfection. Typically it is length divided by 200, so in this case it would be 2.5 centimeters. There might be different values you find in different codes, but Eurocode, for example, gives you hints in there. With this imperfection, I run the analysis again, and I have again slightly higher stresses, and my critical load factor may be increased a little bit from 6.22 to 6.28. But after all, my stress check is okay, critical load factor is greater than 1, and all my results are fine. You see here there's different tables, stresses by cross-section, set of member X location, internal forces. So you can check all your structures, you get the deformations in numerical way, you get your rotation values here. You also have the support reactions. Also, for example, a good information is the twisting moment at the end from the imperfection, for example, that might be necessary to be taken over by the supporting structure for this purling. We can take a look at it also graphically. We have in our RF-FE-LTB a different navigator for results, sigma total, sigma positive negative value, or the sigma equivalent value, and we can use the stress ratio, so 63%. We can also show the deformations, and I can now show this again, and you can see this horizontal restraint due to our rotational spring is doing a good job, and it's helping to stabilize this structure. Before we go over to some questions, I'd like to do some documentation of our RF-FE-LTB. I print this structure, this figure here, to the protocol print. I want to do it window filling. I want to have it on 50% of a page, and when I do it first, I have to open the printout report one time, and it gives me a chance to show you what is in there. So here we have this graphic. RFEM has the regular tables here. There you can flip through and zoom in here. You have the option here to select what you want to have in your printout report. And there is an extra chapter for RF-FE-BGDK, and it gives you all the results that we just manually saw in the module itself. So you find all those tables here again, also with the eccentricities and so on, and all the stresses and all the internal forces as tables. There's one more nice thing I'd like to show you. You can right-click on the structure and get a result diagram. And if you are in the RF-FE-BGDK results, you can check out here a few, for example, the equivalent stress, and then I want to have the global deformation, and then I want to have the internal forces, N, and the shear forces, torsional moments, local, primary, secondary, bending moments, and so on. Everything nicely arranged in one line under each other. You can scroll here if you like to, and you can print this to the printout report. And this is a nice document of all those internal forces. And you can check here everything also graphically in the printout report. Anytime something changes, the printout report will be automatically updated, and it's always actual then in this way. Okay, this completes my presentation, and I think it's time now to take a look at some questions. And I see, let me read what is here. Okay, it takes me a little bit because I have to first check out what is in there. Okay. Okay, there is one. Well, there's one in German. I have to translate it. One question is, what about B to T relation of this thin structure? How can we check this? It's question to shape thin. I go back to shape thin. You have the option to change or to take a look at the width thickness ratios only if you use a certain setting. I go to general data, and then you can check here, check limiting C to T values according to Dann. And if you go to the C to T parts, then you can also check the rule, elastic, elastic, plastic, plastic, plastic. If I do this, or just leave it here, and I analyze it, I run the analysis again, and I take a look at my tables. And of course, I need then for this, I need internal forces. So I check here some internal forces, maybe some bending moment, 5, maybe an axial load. And if I run the analysis again, I get a C to D value check. And you see here actually for each element the the restraint type, if it's supported at both sides. You see the stresses, and you see the allowable and the limiting C to D value and the utilization ratio, basically. This is according DIN, and it's also possible according Eurocode, but it's a different setting. Plastic effective cross sections. Here we go. If I check the effective cross sections, then I can use, for example, also Eurocodes. And if I do this again, no, okay. I have here also the cross section classification according to Eurocode. It leaves out the curved elements because we don't know this type curved elements classification is not a part of Eurocode, so we don't know how to do it, and it's a limitation. But what you see here, the blue lines are the buckling, local buckling parts, and the support condition and so on is all again here. And then at the end you get a classification that we can take a look at. Material. Oh, okay. Problem is here I didn't choose a Eurocode material, but if we would have done this, I would have gotten a classification also for Eurocode, and there are it's possible to do this classification in Eurocode. I will send you this picture with the classification, or maybe I can use another file. Hang on. There is one typical case here. It's a head section, and here it is according to Eurocode, and we use the failing cross-section method, effective cross-sections you can set here. And in this case, we can take a look at the C to D values for each element, and we have here classification. And in this classification, we get here for all the parts for each element. If I click here, for example, it jumps right away to the right table. You get the C to D ratio and all the internal parts and the final class. So if it's class 4, the class of the cross-section will also be class 4. And if I work with effective width, I get a stress analysis only with the effective width in this type of analysis. So I hope this question was answered. Is it possible to make a database of sections? For example, a supplier has 20 types of profiles. Yes, you can do this. You create them inside ShapeThin, and you take them over to RFEM, and in RFEM, if you type them in the table, for example, in the cross-section table, in the input cross-section table, you will be able to read this cross-section. For example, cross-sections, you have to know how it's named, but it will automatically recognize this cross-section by typing it in here. When I import the cross-section from ShapeThin, it is automatically part of the user-defined cross-section library in RFEM, and each cross-section, it's here, each cross-section is also stored inside the RFEM file. So if you send an RFEM file with a ShapeThin cross-section, it will also be there for the user in the other RFEM license. Okay, this was this question. Printing to an RTF file. Typically, you can export each protocol to RTF. So I can file, export to RTF file, or VC Master. There's another program that uses RTF files. So you can use this, you can export it to an RTF file, and then you have a basically Word format, which is not a Word file, which is unformatted, and you can use it for any other use you have, and change it and add your own headers and your own graphs as you like. And of course, you can also copy and paste into this file. So for example, let me try if it, I haven't tried it for a long time. File, export to RTF, ctemp position RTF. Maybe I put it to the desktop so I can find it quick. Okay. Now there's a file, and there is position RTF. I can open in my Word, and I have here the tables all nicely arranged in my Word document. And then you can enter your own header and your own things, and also there should be some graphics which you can use. Of course, you can, what you can also do is you can copy and paste any graphic that you have here. If you want to copy and paste those graphics, you can say Control C, and you can also say Control V, and you will have the graphic here, what you have on your screen, depending on the size of your workspace and so on. So it's all working in any other Windows application. Okay, let's see what else of questions we have. Okay. There's another question whether we can have the effective width according to a German code called DAST 016. At this moment, it is not possible. There will be, of course, ongoing development with ShapeThin, and we will improve this. There is also a new version in work, which major improvement, which also have, we might have seen that there's a difference in the, little bit difference in the user interface with ShapeThin and RFEM, where we also have the same user interface with RFEM, and that will also be available, I would say, within the next year. Okay, there are numerous more questions that I need a little bit time to read through and to think about it. I will go through them and answer them by email. I think our time's also up for the webinar. I would like to thank you for the participation today. I hope you found it interesting, and we hope you can have you back for further webinars. I'd like to point out that there are other information available also on our website, w.dlubal.com. We have videos, we have newsletters. Also follow the Dlubal blog, which will be filled with small hints every day and small tips and tricks that you can find every day on our Dlubal blog. You find it on our website. If you have any question, don't hesitate to contact us or call us. We'll try to answer your question as good as we can. And I'd like to point out also our next webinar. It will be about analysis of cross-laminated timber with RF laminate, and it will also take place on a Wednesday on November 21st, 2012, and we plan to have more webinars later this year. Of course, you can register in the usual way on our website. We will also invite you with newsletters and through Facebook and other social media. And also, I'd like to remind you one more time, this webinar will be recorded or is recorded and will be put online probably no later than tomorrow, and we will also send out some reminding newsletters. Thank you for your participation. I hope it was helpful. I hope you found it interesting, and I hope we can welcome you back to one of our next webinars. And I'd like to say goodbye and have a nice day. Bye-bye.